So this is the video for problem 415. I must admit that this is actually the last video I'm making for this course, and it seems that I've made so many of them now that I'm running slightly out of patience. So this one will be like just a quick walkthrough, more or less. And so let's look at this exercise here. We assume that given p equals p, then n has the geometric distribution as such with these point probabilities. And we assume that p is uniformly distributed, which means that p has density 1 on the interval 0 to 1. So this is the density fp of p. And then we're asked to find the unconditional distribution of n and also the mean of n. So the goal here, goals, 1, what is the probability of n being equal to n, question mark, and 2, what is the mean value of n, question mark. Okay, so let's just try to take a look at this. We want to find the probability that n is equal to n, and using some of the formulas that we have in the book, this is exactly equal to the integral from minus infinity to infinity of the probability that n is equal to n given that p is equal to p. So we take each of the cases and then we multiply by the probability that p will be equal to p, but we don't multiply by the probability because p is uniformly distributed, so we multiply by the density fp of p to p. There are a lot of p's involved. This is for probability, this is for the stochastic variable, this is for the stochastic variable, this is for what we integrate with respect to, this is for what we integrate with respect to. So it's a little bit confusing. Now the density fp of p is equal to 1 on the interval 0 to 1, which means that I can just replace 0 and 1 into the integral bounds, and this just turns into a 1, and then I just have the probability of n being equal to n given that p is equal to p. And that is equal to p multiplied by 1 minus p to the nth to p. And what we want to do now is we want to try and calculate this thing, and a way we can do that is by using integration by parts. That's what I use anyways. So we look at integration by parts, which then gives us this thing here. So you guys are so well versed in integration by parts now that I don't think I need to explain too much of what's going on. We keep the p and we find the antiderivative of 1 minus p to the n, and we minus the integral from 0 to 1, and then we differentiate the p, so that just disappears, and then we integrate the antiderivative of 1 minus p to the nth, and that antiderivative is given as such, so to p. And after we calculate this and spend a little bit of time, we reach the conclusion that this is 1 over n plus 1 multiplied by 1 over n plus 2. So that was the point probability for n equals 1, 2, 0, 1, 2, and so on and so on. Now we're interested in finding the mean value of n. So what is the mean value of n? Just for fun, let's try to use the iterated expectation here. So we take the mean value of the mean value of n given p, because we actually know from an exercise in chapter 2 that a geometric distribution with parameter p has the mean value 1 minus p divided by p. So this is equal to the mean of 1 minus p divided by p. And the mean of 1 minus p divided by p is then equal to the integral from 0 to 1 of 1 minus little p divided by p dp. And we split up this fraction into the part that's called 1 over p dp. And then here we just have 0 to 1, p over p, which is just 1 dp. So we have this thing minus 1. And what is this thing? Well, what thing do I need to differentiate to get 1 over p? The thing that I need to differentiate to get 1 over p is log. So, no, wait. Do I need to? It is log, isn't it? Yes, it is log. Good. It's getting a bit late, but yeah, it is log. So I need to differentiate the logarithm, and we evaluate that in 0 to 1. So the logarithm is the antiderivative derivative for 1 over p, and here we just say minus 1, because the integral of 1 over 0 to 1 is just 1. Now what happens here is we get the log of 1, which is 0, minus log 0, which is plus infinity minus 1, and this is infinity. So that means that n has mean value infinity. And that is okay. We can say that n has mean value infinity because n only takes on non-negative values, which means it's okay that its expectation is infinity. However, when n has expectation infinity, there's not much interesting we can say about it right now at present. So that was that exercise, and apologies for the long pause in the end, but I just needed to be sure. And happy solving and good luck with the exam.